So first of all, I would like to thank the organizers for this opportunity to be in the land of mangoes. And I'm going to speak about, as written here, denominators of rational Drinfeld associators. So it's a joint work with Anton Alexeyev and Masha Podkopayeva. So I suppose most people know what denominators are. There might be some people who don't quite know what Drinfeld associators are. So I'm going to tell you. But first, I should provide some excuse for speaking about this on this conference of Poisson Geometry. So I'll probably first tell you what they are good for, what are Drinfeld associators good for, some applications. So one big thing is deformation quantization of Poisson manifolds. So there is a procedure invented by Tamarkin, which starts with a Drinfeld associator, then there is a lot of work, and at the end there's a formality morphism, which can be used to turn Poisson structures to star products. So this is due to Tamarkin. There is something older and much more simple, much more direct, which is quantization of Lie by algebras. So this is work of Ettinghoff and Kashdan, and that's in turn based on the original work of Drinfeld, where it was, I will not write it down because it's just too long, too incomprehensible, but there is quantization of quasi-triangular, quasi-Lie by algebras to quasi-triangular, quasi-Hopf algebras. Even though the words are very long, actually it's the simplest thing. So maybe I'll write what is somehow behind and how does Drinfeld associators appear most naturally. So it's a third deformation problem where you now it's deformations of symmetric monoidal categories to braided monoidal categories. So you start with the symmetric monoidal category, you choose some first order deformation of the symmetry to braiding, and then the Drinfeld associator will provide you some true deformation into some true braided monoidal category. So it's some universal solution of this deformation problem. So these are all somehow quantization problems. There are all kinds of other problems connected with quantum groups, like quantization of R matrices, and you can imagine whatnot. So it's quite, I hope it looks quite appropriate to speak about associators, maybe. And maybe I'll list you one more application which is not connected with deformation, at least it's not very clear. So there is a fourth application. It has applications to not invariance. So there is something which is called Kontsevich integral, or we can just call it Kontsevich not invariant. So starting with an associator, we can build an invariant which is universal in certain category of invariants and in certain type of invariants. So it's universal among so-called perturbative invariants. So after all this advertisement, what actually is a Drinfeld associator? So I wrote you a definition over there. Just to basically, the definition says that it's something given by very concrete equations. So it's a solution of some very concrete equations. That's one thing. The second thing is those equations are somehow look completely random. So I'll try to also explain you what those equations are. But let me just read what it is. So you need to choose some field of characteristic 0. If you wish, that field can be real numbers. But later on, we're going to use rationals anyway, so it's some field. Now, Drinfeld associator is a formal power series in two non-commuting variables. So it's an infinite bunch of numbers, those coefficients that we are looking for, and satisfying some equations which are written here. So one thing is that it's supposed to be group-like, which means just there is exponential of a Lie series, or exponential of something which is built out of commutators. It satisfies one more equation that I forgot to write here, which is 5xy times 5yx is equal to 1. And then there are two somewhat more difficult equations. One of them is called hexagon. That's what's written here. There are six terms in that formula. That's why it's called hexagon. And then there is some yet bigger equation, which is called pentagon. Which is form 5 times 5 is equal to 5 times 5 times 5. Maybe I should explain you who are these variables that appear here, because now this is no longer written in a completely free algebra. It's now in some algebra where there are some relations. So those Tij's, they satisfy certain relations, like Tij commutes with Tkl, provided all those indices are different. So if and there is one commutation relation which says something about what happens if two of those indices are the same. So there is Tij commutator with T ik plus T jk is equal to 0. So this is basically just to impress you. So what's going on? And there are some relations on top of that, like Tij is the same as Tji, and I is always supposed to be different from j. So there is no Tii, so to say. But in the end, those equations are very concrete equations for coefficients, for unknown coefficients of this pi, and you can try to solve them. Just the trouble is, of course, that there is infinitely many of them, but still. Once you have a solution, you have all those wonderful applications. So I'll tell you, as I promised you, I'll try to tell you somewhat later what it all means. But now let us ask a question whether those Drinfeld associators actually exist. Right? Otherwise, they might have quite many applications. So, say for over C, if you take for your field complex numbers, this is the oldest known associator. So there is something which is called, there is some explicit formula for a certain associator, which is called Knižník-Zamolčíkov associator. Coefficients are multi-zeta values. So this is something quite nice. There is out of that you can cook up something which is over R, but there is maybe one other example over R which is more interesting. So it happens if you compare deformation quantization procedure as provided by Tamarkin with deformation quantization approach of Kontsevich. Because Kontsevich gave a concrete formula. It doesn't use an associator as an input. It is just one formula. So if you compare those two approaches, then it's quite probable that you can pull out some associator out of this conservation construction so that when you plug it here in, you get back this Lamarckian construction. It is indeed possible. And so there is something given, okay, again explicit associator which was first found by Alexeyev and Torosyan. So here those coefficients were multi-zetas. Here coefficients are some integrals over configuration spaces of points in a plane, just as those integrals that appear in conservation formulas. Mm-hmm. So here we have two nice explicit examples. Now we can ask what happens if k is equal to q. For some reason it is a very interesting question. Maybe I will get to why this is the right question to ask. But what is known here? So it is known that associators exist. And the only known, at least as far as I know, the only known proofs of this statement actually use existence of associator either over real numbers, over complex numbers, or over whatever other field. So at least so far to prove that there exists a rational Dirichlet associator, you first need to have some transcendent construction, which is a bit strange, right? There are some concrete algebraic equations. There is a statement that this system of algebraic equations has a rational solution, but the only known proof goes through knowledge of some transcendent solution, of something given by some completely non-algebraic methods. There is maybe one more thing that I can tell you. It might be difficult to solve all that system of equations for infinitely many coefficients. So what you can try, you can try to truncate it. You can try to take power series, but only up to some order, and consider all those equations only up to that order. Mm-hmm. So if you have a solution of that, you can call it a partial Dirichlet associator, right? So it's something which is then really a noncommutative polynomial up to some order, and all those equations are valid only up to that order. And there's a statement that actually any partial Dirichlet associator can be extended to a full Dirichlet associator. So I can say something like that. Plus, there are no obstructions to extension. Meaning that you can solve it up to order 7, and then there's a theorem which guarantees you that you can then extend this solution to order 8, and then to order 9, etc. So this looks like something that should be solved by some cohomological methods, right? So there is the statement, there is no obstruction to extension to the next order, but unfortunately nobody was able to compute that cohomology. The only proof of this statement is still through knowledge of some explicit associator. So this would be a wonderful, of course, announcement now that here you have an explicit formula. But, well, we don't. So what should I talk about then, right? So let me instead ask some somewhat stupid question. So what would happen if you take for k z? Well, z is not exactly a field, but well, if nothing better happens, so well, so how does it work? In fact, any associator always starts with 1. That's fine, that's an integer. Then there is 0 for the linear term, but then for any associator, it happens to be so that there is 1 over 24 times commutator of x with y. And the third term is already not determined. The third term can be chosen to some extent, so that is not unique. But certainly 1 over 24 is not quite an integer. So there is something in third order. Maybe I can tell you that by some strange coincidence, the fourth order is fully determined. So it's for all associators, there is this fourth order term is the same. Let me see. There is something like 1 over some horrible number, 5760, and times something. I'm not going to write down that something. It's just something of order 4. So this is the common denominator of the terms which appear in degree 4. So these things are not exactly integers. And we can peek a bit about at what happens next, what happens in arbitrary high orders. So it's a relatively easy exercise to show the following statement. That if you choose whatever prime number p, you can ask whether 1 over p appears somewhere in this among the coefficients of the associator. And there is a relatively easy statement. So this easy statement follows more or less directly from this hexagon equation. You can do it more or less by hand. So if p is a prime, there is a statement that 1 over p must appear somewhere in orders which are less than equal than p minus 1. So we cannot have that all the coefficients of in degree 0, 1, 2, up to p minus 1 are p integers. So there must be some 1 over p there. Okay, so that's what is doable by an easy calculation. So now I can tell you the theorem. So there is a theorem. In an easy way, the theorem says that actually there exists a rational Drinfeld associator such that the first 1 over p appears exactly at this degree p minus 1, and moreover it appears with power 1, so there is not 1 over p squared. But the theorem is more precise because it says exactly about what orders you can expect, what degrees of p. So I'll write it something like that. So this is our theorem, which says that there exists rational associator such that now for every p, if you look at the multiplicity of p, so if you look at vp of the coefficients which appear degree n, so this coefficient of degree n, I'll write minus because we're looking at the multiplicity in denominator. So this stuff is bounded by, and there is some linear expression now which might be surprising. I'll comment on it in a bit. So it's p over p minus 1 squared times n minus 1 over p minus 1. And plus, this theorem continues a bit. As it was here, there is not just an existence statement that But in principle, an associator might be just if you know that it exists, it might be not computable. But there is an extension of the theorem which says that if you compute it up to arbitrary order, you can always extend. So there is always hope to continue. So there is the same statement here. So there is plus no obstruction. So from here you really get that this valuation is less than 1 if n is less than p minus 1. So really the first 1 over p appears at this degree, and it is exactly equal to 1 then. And also if you check these coefficients, it is somehow 24 is, I believe, 2 power 3 times 3. And this stuff, 5760, that's equal to something completely horrible. 2 power 7 times 3 power 2 times 5. At least here it happens that those exponents are exactly as predicted by this theorem. So we cannot really say that this is the best estimate that one can get, but at least there are some checks where it looks that we're getting quite close. So now, if you want to find a rational difference associated with a computer, you can always look for things with this bound. So this is basically you can work with integers because you have a bound for denominator. Yes?
Do you have the same bounds for the logarithm of phi as for phi?
Yes. Yeah. Maybe I'll comment a bit on that. So what does it mean to some extent? Maybe for that logarithm, or why this is not very far from one can hope for, or one can best expect. There is another power series. Say, let us look just at exponential of x. Yes, this is something like sum x power n over n factorial. So here we have some 1 over n factorials. And what are the periodic valuations of n factorial? So Vp of n factorial, that's bounded by, and there's equality infinitely often, and the difference is only logarithmic or something like that. That's bounded by 1 over p minus 1 times n minus 1 over p minus 1. So you see, this stuff is slightly bigger than 1 over p minus 1. So we get slightly worse estimate than exponential, than for exponential, but it's not very far. So what is the meaning of this? Yes, but because I told you that one can show that there must be some 1 over p somewhere in those orders, and since now we're an associator where there are no 1 over p's. Well, okay, so yes. So what is it good for to have such an associator? Well, besides for those computer experiments, which we didn't perform, but we hope somebody will. You can now take an associator which satisfies these bounds and plug them into those applications and check what you get out of that. So, for example, an associator which satisfies this kind of bound is convergent in periodic topology for every p with some non-zero radius. So if you do it, if there are no other horrors appearing in your problem, you will get that in place of a formal deformation, you have some analytic deformation in the neighborhood of 0 for every periodic field. That's one application. Well, another application is just much more easier. You just look at denominators that appear, and you get some bound on denominators. For example, for this concept is not invariant. So maybe we'll talk about it slightly later. So now I would like to explain a bit what actually is an associator. It is a solution of some equations, but that's not very helpful. And so maybe the quickest way of saying it is what I told you there, so that an associator is a universal way how to deform a symmetric monoidal category with some first-order braiding to a braided monoidal category. It's very fast to say, but then maybe not everybody gets what's going on. So let me be somewhat. Let us forget maybe about monoidal categories, and let me rephrase all those things in terms of some braids, because associators are really about associativity and braids. So there is something going on like that. So first, let me remind you, there is something called pure braid group. So elements of that pure braid groups are braids. Where this pure means that we require that every strand returns to its original position, that there is no permutation of these final points. And the group operation is by concatenation. So let us call it PBN, where n is the number of strands. Now, this pure braid group can be described explicitly by generators and relations. It's quite easy. So let me write you what is a nice set of generators. So there are some generators called Xij normally, and they look like this. So I'll try to just draw it. So this is the ith strand, and this is j strand. So I is less than j. So you go with i's around j's, and then the strand from behind. So these are some nice generators. One can write down explicitly the relations. I'm not going to do that. It's not terribly important for us. But out of that, out of this pure braid group, you can build a Lie algebra in some formal way. So it is corresponding multiple Lie algebra. I'm not going to explain very formally. Let's just do it like this. So let's write formally that Xij is equal to exponential of psi ij. So this is the definition of psi ij. And then the relations satisfied between those xij's are turned into some relations satisfied by those psi ij's. So there are going to be some Lie relations. That some Lie words, or rather some Lie series, in terms of those psi ij's are equal to 0. So that way, we have a Lie algebra. Let me call it PBN generated by those ij's. So it's a rather difficult object because those relations are really difficult. You can imagine that you need to take logarithms, so you get all kinds of Campbell-Hausdorff series inside. But there is some degenerate version of this PBN, So out of this PBN, we produce some Lie algebra, which is called Tn, which is the graded version of this PBN. So the idea is that you just keep the lowest order terms in your commutation relations and you remove everything which is above. So that way you get something which is probably much easier. And in fact, it's something that was already written on the blackboard. So let me write it again. So this Tn is generated by things which are now called Tij's. But there are those psi ij's just with those simplified commutation relations. And now this, when you keep only the lowest order terms in those commutation relations, you get exactly those relations that I wrote. So like Tij commutator with Tkl is equal to 0, and Tij commutator with Tik plus Tjk is equal to 0. And then out of this Lie algebra Tn, you can produce a group. You just take the exponential group. Of a group Tn. So maybe to be slightly more precise, it's a Lie algebra over what? So we need to choose a field. You can choose rational numbers because everything is defined over rational numbers. But in principle, it depends on some field. It's just the coefficients that you choose to use. You can use rational numbers. It's okay. So this group is some kind of, in a way, simplified version of this pure-Bay group. And we can ask whether there is a morphism which would go from PBN to this Tn. Okay. And a naive way to do it, which doesn't work, is that we just replace those psi ij's with Tij's. So let us try to send xij's to exponential of Tij's. So is it a morphism of groups? Well, not. Well, that's certainly not surprising that this is not a morphism of group, since the commutation relations between those Tij's are not the same as the commutation relations of xij's. They are just only to the lowest order. But the situation can be, we can still resolve the problem. And the idea, I'll draw it quickly here. So the idea is to still, when you see something like this, where here is I and here is j, you're still going to write exponential of Tij, well, divided by 2 because there is only half crossing here. But the idea is now that you do it only when those strands are close to each other. And whenever you see something like Ijk, I'll draw parentheses here, and Ijk, parentheses here. So these are close and these are close. And so this j goes from I to k. Whenever you see something like that, you need to associate to it some element of this group Tnk, and this element is going to be somebody who is, in this case, it's in T3. Okay, and if the thing that I described here informally actually works, then you would call this phi a Drinfeld associator. And if you just work out what those relations actually mean, then you end up with all those equations that I wrote here. Maybe I'll try to explain you where this pentagon comes from, and then I'll tell you some precise statement about that, because this is not very precise. So I just erase this pentagon equation, and I'm going to write it in a different way. So what is the idea there? So you maybe start with I, J, K, L, and use the bracketings as here. So I and J are close, and K is close to them, and L is far apart from them. Now we start to rebracket these things. So we're going to use these elementary operations. What can we do? We can, for example, move the brackets. We can move this J from I to K. So we can have something like I, J, K, and then L. Then we can move the brackets again. So we can have something like I, J, K, L, and finally I, J, K, L. So at every step I just use this. I just use the rebracketing in this form. That you have some I, J, K, and in the end you have I, J, K. But there is another way how to get from here to there. So you can also take this ij as a single object and pass to ij kl, and then from here with a single rebracketing you can end up here. So these are two ways how to get from here there, and they give you the same braid, but this is the same trivial braid, so to say. So you need to get the same result. And this pentagon equation just says that the product of these three phi's is equal to the product of these two phi's. That was it. And now there is a theorem which says that actually these pentagon and hexagon equations, they correspond to some simple diagrams, like to this one, and then there is something corresponding to the hexagon equation. They are sufficient to ensure that it works for arbitrary braid. So now I can write you some precise statement about what I mean. The precise statement is going to be slightly less comprehensible, but it's going to be true. So how does it work? So first of all, let us introduce a groupoid. For every n, we introduce some groupoid, which is called braids n. So it depends on natural number n. So what are the objects? Those are bracketed permutations of 1, 2, up to n. And what are morphisms? Morphisms are simply braids connecting corresponding numbers. So I'll draw in an example of what I mean by connecting corresponding numbers. So maybe something like 1, 2, 3, 4. And now choose whichever braid which connects 1 to 1, etc. For example, I think like that. Right? You can compose them as you compose braids normally. So that's it. And then, so this is a sequence of groupoids. Now, this sequence of groupoids form actually an operand. So what is the opera decomposition on pictures? On pictures, you just take, if you want to substitute some braid for this 1, so you just remove the strand which corresponds to 1 and place in the other braid, which is made thin enough to fit somewhere in the neighborhood of 1. That was a quick description, but there is a better description maybe. This operand is the operand of operations that you have in braided monoidal categories. Right? So a braided monoidal category is by definition an algebra of this. So out of that you can say who is this. So algebras is equal to, are the same as braided monoidal categories. Now those Tn's, they also form an operand. Groups, or if you can say that these Tn's form an operand of free algebras. So these are more or less the operations that you can find in symmetric monoidal category where you have some infinitesimal braiding. And then an associator is the same as a morphism of operands which goes from braids into T. So that's roughly. I hope this was incomprehensible, at least for many people. But in the end, the important thing is that if you have a braid, and you choose some bracketings on the endpoints, you can associate to a braid always an element in that group Tn. You simply associate to this kind of move, this exponential, and to that kind of move, this phi, and so you build your braid out of these elementary operations, and that's it. And the statement is that when you do it, the result depends only on your braid. So now, what should I do? Maybe I can tell you something about this concept which is not invariant. So what did we have? So we have, if you have a braid, we can associate to it some element of Tn. So it is a braid with n strands. But now we're interested in knots. So let us suppose that we actually have a knot, which is given. Now a knot is going to be given in terms of operations like this or like that, but there are also going to be some caps. So you can have something like that or also something like this. So maybe I can. So suppose that you have a knot, you take its generic projection into the plane, and then try to build it out of operations like this. So maybe you start here and here, then you move here, then you can cross, you can come back, I don't know, you can do something like this. This is not exactly knotted, but you can imagine that with a bit more of work, you can get some actual knot. And so what happens if you try to associate something to a knot using our prescription? So we want to, for every crossing, we want to write something like this. For every rebracketing, we want to write phi. And then let us decide that for everything like that, we don't write anything. So we just write 1. Well, does it make sense? So it makes sense in the following way. So we're going to every knot we're going to associate a chord diagram. So you take the knot as just an abstract circle, but in that circle we're going to have some chords. Something like this. I'll be more precise in a moment. So how exactly does it work? So say whenever you have a crossing, you associate to it what is drawn here, but now you interpret this Tij as a chord between these two strands. So you're going to write something like this, that it is exponential is equal to 1 plus there is 1/2 here, so there is 1/2 of this, plus there is 1/8 now when there are 2 of these Tij's plus etc. So this is what you do for every crossing, and then for every rebracketing, you're going to write phi in Tij and Tjk. So you're going to draw some chords like that. Now, how does it make sense? It does make sense if you make some precise definition. So I should tell you exactly what a chord diagram is. So it's a linear combination of things like this. So it's a circle. Whatever systems or sets. With chords. But modulo some relation. So modulo. Those relations are going to correspond exactly to relations that you have between Tij's. So what is the relation? I can maybe if we draw 3 parts of that circle, and if you write this equation which says that Tij, comma Tik plus Tjk is equal to 0, that is going to give you something like this minus this plus this minus this is equal to 0. That's exactly what is drawn here, what is written here. So these are some kind of vector space that you get here. It is also a commutative algebra, but I will not speak about that. But the thing is that actually the chord diagram that you build using an associator doesn't depend on the particular representation of the knot. So it is really a knot invariant. I was cheating a little bit. We need to make some normalization which comes from the number of caps, but I will not tell you exactly. It's not very important. So in this way we can get some knot invariant. It is a universal Vassiliev invariant. This invariant actually doesn't depend on the choice of phi, which is slightly surprising maybe, but still it requires some choice to build it. And now with our theorem, we can say that we have a theorem about estimate of denominators of this concept is not invariant. This estimate is exactly the same estimate as was written for this phi. Right, so those coefficients are some rational numbers, and now we have a rather nice estimate on their denominators. I have still maybe something like 4 minutes or so. So that should be, as Marius explained us, enough for the proof. So remember, the theorem said that there exists a rational different associator with some particular bound on denominators. So how do we find it? So the proof goes through several steps. So first, we have some theorem which allow us to construct associators out of elements of Grothendieck-Teichmüller group. So there is I should explain you a little bit about who is this Grothendieck-Teichmüller group. So these things are automorphisms of these operative braids with some minor complication that we need to take some K pro-important completion, but ignore that. It's not important. So how does it work? This operative braid is anyway generated just by 2 moves. Those are those 2 moves that I was drawing there. So there are only 2 things. This and that. Now we can try to replace it with some other thing. Right? So if it's an automorphism, this move has to be replaced with some other move, and that one with some other move. So if this is ij, and this is ji, so how can you replace this? So those I and j need still to be reversed. The only thing that you can imagine is that you're going to repeat this half twist lambda times. So we do it lambda times, when now this lambda is equal to 1 plus 2m. And if you don't do any completion, then this m has to be an integer. The trouble is that then such things don't exist, so we'll see. And this stuff has to be replaced with, it's going to be some other, so this is ijk, so this is going to be some other pure braid. One can check that these 2 strands actually stand still, and that it's only this stuff that goes around. So it's an element from free group with 2 generators. So an element of GT is a pair. So it's a pair lambda, where now this lambda is actually in K, or K star. And something which is from a free group with 2 generators, row input and completion, in such a way that it preserves the operatic structure, so it needs to preserve the defining relations which are exactly pentagon and hexagon. So there are some equations satisfied by that. Now since the Grothendieck-Teichmüller group acts on this operand, and an associator is the same as a morphism going from here to tk, then if you compose action by some element with an associator, you get a new morphism, so a new associator. I can maybe write down the formula, which goes like this. So lambda f acting in phi is equal to, so this is going to be fast. Okay, so let's call it phi prime, and this phi prime lambda x lambda y is f x phi. So just looking at the pictures, you can build some formula. So this new associator actually comes with rescaled variables because we rescale the braiding here. So therefore, we're going to associate with this the e power lambda tij. That's why this lambda appeared there. And now you can ask a question: when you have a pair lambda f, whether there exists an associator such that phi is equal to phi prime. And the theorem says that if lambda is not root of unity, then there exists exactly one phi such that phi prime is equal to phi. So this phi is given by this explicit formula. So you can compute it step by step. It's rather easy. And so we can get our associator provided we had some nice element of Grothendieck-Teichmüller group. But then it becomes even worse. So we need some source of elements of Grothendieck-Teichmüller group. But there is one wonderful source. Which goes as follows. So if you take the group of automorphisms of algebraic numbers, then there is some homomorphism going from here into GT. Now I'll write here periodic numbers. So now for our K, for our field, we choose periodic numbers. This homomorphism is rather difficult. But at least we can say exactly what happens if you take a G, so associate to that pair lambda f. We can say who is lambda. This part is easy because lambda is equal to the periodic cyclotomic character of G, meaning that when you take a root of unity, then G acting on psi is equal to psi power lambda. And we know not only that, but we know also that this lambda is actually an invertible periodic integer. We know not only that this lambda is an integer, an invertible, but we know also that in some reasonable generators, this f has integer coefficients, I mean periodic integers. And therefore, you can imagine that if lambda is some integer and coefficients of f are integers, then if you plug it here and compute phi, you get something with some, maybe not integers, but with some estimates on denominators. So more precisely, if you choose if you choose lambda such that the group generated by lambda is dense in the group of invertible periodic numbers, then we get exactly our estimate. We can choose whichever lambda because, well, this is the Galois group of this corresponding field is just equal to this. So out of this, we can say that we have a associator but with coefficients in QP, satisfying some estimates. And then we take all these associators and do some, basically use Chinese remainders theorem or strong approximation theorem, or however we call it, to build up a rational Dirichlet associator. Okay, so that was the proof, and thanks a lot.